So Unit 18 is all about polygons, and we're going to jump here on Box B. Box A is a little bit of an investigation that I'll leave for you guys to do on your own. And in Part B here, we're just going to talk about some of the terminology around polygons. So you've got this on your lesson sheet there, I think. What is a polygon? Well, basically, a polygon is a closed figure formed by joining 3 or more line segments at their endpoints. So basically, you take straight lines, connect them together, take as many as you want, just connect them at their endpoints or their vertices, and make them all, do enough of them that they come around and they form a closed figure. And as long as those lines are straight lines that you're connecting together, you've got yourself a polygon. Okay? How do we describe polygons? Well, if all of the sides are the same length, we say that the polygon is equilateral. Lateral just meaning sides, equilateral meaning equal sides. I don't know if you have these red words on your sheet, so you might want to write them in there. If all angles are the same size, then we call them equiangular. Okay, equal angles, all angles the same. If a polygon is both equilateral and equiangular, so it has equal sides and equal angles, we call it a regular polygon. So let's take a look at these 2 polygons that we've got right here. First thing you got to know about polygons is we give them special names depending on the number of sides. So right here we've got a 1, 2, 3, 4, 5-sided polygon. What do we call a 5-sided polygon? You guys probably know this one. Jackie. This is a pentagon. Then it only has 4 sides. 5 sides. Now, take a close look at this pentagon. Is this pentagon equilateral? What do we think? What does equilateral mean? It means all the sides are the same length. Do all of these sides look like they're the same length? You might not be sure, but what if I do this? What do these tick marks mean? Chris? Yeah. So if I do it like this, it becomes pretty clear that this thing is equilateral. Is it equiangular? Now this should be clear kind of from the diagram here. Is it equiangular? Michette's shaking her head. How do you know? Yeah, so it is not equiangular. Is this a regular polygon? Why not? Yeah. It has to be both equiangular and both equilateral and equiangular for it to be regular. So this is not regular. All right, let's take a look at the other polygon over here to the right. How many sides does this one have? Let's name it first. 1, 2, 3, 4, 5, 6, 7. 7-sided is called a heptagon. 7 sides. What do you think about this one? Is it equilateral? What do you think, Andrew? Equilateral? Yeah, those look pretty much the same. Okay. What about equiangular? What do you think, Liam? Equiangular? Yes? No? Oh, this one over here. Yeah, that's equiangular. So if it is both equilateral and equiangular, what can we call it? We can say that it is a regular polygon. Okay. Now, the point where 2 sides meet is called a vertex. So a point like this right here, this is a vertex. Over here, this is a vertex as well. Okay. A diagonal is a line segment that joins 2 non-adjacent vertices. So if I take one vertex here and I draw a straight line going to another vertex, we call that a diagonal. And what we're interested in next is we're interested in the number of diagonals that can be drawn from one vertex. So if I start at this one vertex, I can draw one diagonal. I could also draw a diagonal kind of like that, okay? If I always use this vertex as a starting point. So if our figure has 1, 2, 3, 4, 5 sides, we can draw 2 diagonals. What if we have 7 sides in our heptagon over here, and we start from this point right here, and I start drawing diagonals? There's one, there's another one. Can I draw more? Yeah, I can draw one up like this. I can draw one like that. So in total, I've drawn 1, 2, 3, 4 diagonals. So what's this? 7 sides, 4 diagonals. Okay. So do you think there's a relationship between the number of sides and the number of diagonals? Liam? Yeah. So let's say number of diagonals equals number of sides minus 3. Okay, that makes sense. All right, and now let's just continue on here into box C. In box C, we're looking at the interior angles of polygon. And we'll also take a look at the exterior angles first. And we'll start off with something basic here. The sum of the interior angles of a triangle is 180 degrees. You guys learned this back in grades 7 and 8, so this should be old news to you. What we want to be able to do in this course is we want to be able to find the sum of the interior angles of any polygon. And to do this, we can imagine dividing it into triangles by drawing diagonals. So I've got a shape here. I've got a hexagon. Let's start at one vertex and divide this thing into triangles by doing diagonals. 1, 2, 3. Okay, 3 diagonals because I got 6 sides. 6 minus 3 means I can draw 3 diagonals. Now, and of course we're doing this from one vertex. By drawing these diagonals, I've taken my hexagon and I've divided it into triangles. I've got 1, 2, 3, 4 little triangles inside my shape here. If each of these triangles has the sum of the interior angles of each triangle is 180, we can think of each triangle adding 180 degrees to the sum of the interior angles of our hexagon. So if we want the sum of the interior angles here, we do 4 times 180, 4 triangles, each one gives us 180, gets us 720 degrees. So the sum of the interior angles, all of these interior angles right in here, okay, on the inside of our hexagon, R is 720. The sum of the interior angles is 720. Now, we don't want to have to draw our shape every time and draw those diagonals. We want to think of this in terms of a relationship or an equation here. So we can express this as an equation relating the sum of the interior angles S and the number of sides. Well, on the last page we said that the number of diagonals we could draw, well, not diagons, diagonals, was the number of sides minus 3. When we're drawing these diagonals, when we drew 3 diagonals, we got 4 sides, 4 triangles, 1, 2, 3, 4. So we always end up with one more triangle than the number of diagonals. So the number of triangles we end up with is going to be 1 more than n minus 3. It's going to be n minus 2. Okay? This is always 1 more than the number of diagonals. Well, if each one of our triangles gives us 180, then the sum of the interior angles is going to be 180 degrees times the number of triangles, times n minus 2. So if we just take the number of sides, subtract 2, and multiply by 180, that'll tell us the sum of the interior angles of our shape, whatever our shape is. Make sense? Okay. So this is something, this is one of the formulas that you're going to need to remember from this unit here. So let's apply this here to a couple of questions. You got these questions on the back of your sheet. Find the sum of the interior angles of a nonagon. First thing we need to know is we need to know the number of sides. How many sides do you think a nonagon has? Jackie? 9. 9-sided figure here. So if we want the sum of the interior angles, we want to use that equation that we just came up with. The sum is 180 degrees times n minus 2. So we know what n is. N is 9, so let's plug that into our equation. 180 degrees times 9 minus 2, or 180 degrees times 7, and then we just punch this into our calculator. 7 times 180 degrees gives us 1,260 degrees. Next question here. Find the size of each interior angle in a regular octagon. Okay. We've got a picture of an octagon down here at the bottom that we're working with. So this is a regular octagon. How do we know it's a regular octagon? Andrew, how do we know? All the angles are the same, and what else? All the sides are the same. Okay. So we want to find the sides of each interior angle. We're going to start by finding the sum of the interior angles. And to do that, we're going to use our formula, n minus 2 times 180 degrees. All right, so what's our value of n here? If we're working with an octagon. N is always the number of sides. How many sides do we have here, Andrew? 8 sides. So let's put this in here. We're going to have 8 minus 2 times 180, 6 times 180 degrees. Punch this into our calculator. 6 times 180 gives us 1080 degrees. Okay. Are we done? No, because it's not asking us to find the size of the sum of the interior angle. It's asking us to find the size of each interior angle in a regular octagon. So looking at this octagon down here, how many angles, interior angles, do we have? Liam, how many angles are there in there? 8. Yeah, it's always the same as the number of sides. And what do we know about these angles? Well, we know that they're all the exact same size because it's a regular octagon. So if we just take our 1080, divide it by 8, that'll tell us how big each angle is. N equals 8, so that's telling us that there are 8 interior angles. So 1080 divided by 8, we punch this into our calculator, gets us 135 degrees. So each angle must be 135 degrees. Okay, last question here. We're still working with our octagon. Find the size of each exterior angle in a regular octagon, and then find the sum of all of the exterior angles. So first off, what do they mean by an exterior angle? Well, an interior angle is inside our octagon here. Label this as interior. We get an exterior angle by taking one of our sides and extending it like this. This angle here is an exterior angle because it's on the outside of the triangle, of the shape. Okay. And if we extend all of our sides just a little bit, we can see that we get a whole bunch of exterior angles being formed. And I'll just put them all here in blue. Down, 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 down. Yep. Okay. So if we have 8 interior angles, we have 8 exterior angles, one for each. So first off, if we want to find how big one exterior angle is, let's just sort of zoom in on this first one that I drew. We've got a line like that. One side of our octagon goes up like that. We've got our interior angle in here. We've got our exterior angle out here. We know how big our interior angle is because we found it up here in the previous question. It's 135 degrees. How can that help us find what the exterior angle is? What do we know about these two angles here that sort of form this straight line? Chris? Yeah, this plus this gives us 180. So this angle in here, let's just label it as x. To figure out what that is, we're going to do 180 minus 135 degrees. 180 minus 135 is 45 degrees. So that angle, that exterior angle there, is 45 degrees. Now, how can we figure out what the sum of all of the exterior angles are? Well, how many exterior angles do we have? 8. Are they all going to be the same size? Yeah, because this is a regular shape. This is a regular octagon here. So, whoa, what's going on there? I got to move this up. And I can't. Okay. Okay, let's try it. So let's just say the sum of, oh dear. So the sum of the exterior angles is just going to be 8 times 45 degrees, 8 times each exterior angle. And if we do that, 8 times 45 degrees gets us 360 degrees. Now, this is true of any kind of polygon that you have. No matter how many sides, the sum of the exterior angles is always 360 degrees. So let's just say this is true for any polygon. Okay? Sum of the exterior angles is always 360 degrees. And the way you can think about this is if we go back to the picture of our octagon here, and I imagine sort of starting, I'll do this in green, starting right here, I've got this, 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 and then I'm back to where I started. I've essentially gone all the way around the outside of my polygon. Well, if I go all the way around and come back to my starting point, I've drawn a little circle. How many degrees are there in a circle? 360 degrees. So all of these little steps that I've taken around the outside have to add up to 360. And that's where we're going to stop.